I'm very happy to speak in this conference. So today I'm going to talk about a work which is in collaboration with Katie Gittins, Caroline Gordon, Magda Khalile, Mary Sandoval, and Liz Stanhope. So, I will start. Oh, I want to start just talking a little bit about the motivation of this work. So just let me briefly tell you that maybe some of you know what the orbifolds are, probably most of you, but if not, I just want to sell the idea here now in this talk that orbifolds are beautiful mathematical objects, and which lie in not just beautiful, but they're very interesting because they lie at the intersection of several fields in math, including, of course, differential geometry, algebraic topology, algebraic geometry, algebra in general, and mathematical physics. And one way to think about orbifolds is as a generalization of a manifold in some sense. So locally, we can think of an orbifold as the quotient of Rn by some finite group. So, and in general, for instance, these orbifolds arise, for instance, as quotients of, as I'm showing here, say of, in some cases, they arise as quotients of, say, some wallpapers by the group of symmetries of the wallpaper, as I'm showing in this picture. So, for instance, this picture was taken from the book The Symmetries of Things by Conway. And in here, so we can say that, well, we can see that here we have a wallpaper, which is very nice, very pretty, and we are explicitly showing so the symmetries that we can find. So, for instance, in here, in the blue points, so we can see that we have here, there is a C3 is acting in this wallpaper by rotations by 2 pi over 3. Then if we can take again 3 planes, and well, we can have these mirror reflectors. And so we have also here at this point and this intersection where we have this axis where we can reflect the wallpaper. So there is a special point that we call dihedral point. So if we quotient this wallpaper by the symmetries, the group of its symmetries, then what we obtain is this basically this orbifold. Yeah, so this orbifold, then we can see that it captures the symmetries that we can see in this beautiful wallpaper. So here, for instance, we can think of orbifolds as generalizations in the sense that also are kind of manifolds with some singularity. So in this case, at the bottom of this orbifold, we have a cone point, which is an isolated singularity. At the top, we will have again another singularity that is called the dihedral point. And this part, which is kind of like the upper part, we can see that this is just again is obtained as a singularity by these reflections. So this is, of course, an example. I just want to show some other examples of the things that we can find for orbifolds. So again, we have another beautiful wallpaper. So in this case, now we have at these blue points, the symmetries acting on this wallpaper. So we have here, basically in each of these points is the group C2 acting just by rotations. And then the quotient space that we obtain is the one that appears in the left-hand side of this picture. And basically what we have is 4 isolated singularities which basically are obtained because these blue points are fixed by the action of C2. But okay, this is not just the only case. Wallpapers where we can find, for instance, where we can construct orbifolds. But now, for instance, in here, I'm showing now the case of spheres. So again, we can think of putting a sphere, some nice decoration, and then try to see what the symmetries are in this decoration, and then quotient this sphere by the action of the group of symmetries. So here, for instance, if we take the North Pole and the South Pole, then and we we pass like two planes through the sphere that pass through these two south and north pole, then what we will have is kind of this wedge, but just like at the outside of the wedge. I think of it as a kind of an orange, but just I think about as just the outside of the surface on the orange. So this will be kind of a wedge, just in the surface. And here, so we will have here in north pole, the south pole will be these singularities. This will be also dihedral points. And here we have, of course, these will be reflections, and this will generate our singularities. Now, if we add, for instance, more decorations in the right-hand side, I'm showing now what happens, for instance, if the upper part is have the same decoration as the lower hemisphere of the sphere. And so when we take this quotient, then what we get is kind of half this wedge that I was saying just some minutes before. Okay, so then if you indeed look at whatever other nice wallpaper in the internet, you can play with the symmetries of the wallpaper, and then try to consider the quotient space, and then these will give you examples of orbifolds. Yeah, so these are some particular examples. But okay, so what I want to say basically is that orbifolds are beautiful and also capture a lot of symmetries of certain objects. All right, so but then so the idea of this talk, so I want to answer to relate this orbifold with the following to the spectral geometry with the following question: can we hear the shape of a singular orbifold? So as we probably most of you know, like the tools of spectral geometry have been applied very much for the case of manifolds, which are indeed, as we will see later, a particular case of orbifolds. But indeed, we can apply the same tools of spectral geometry for more general orbifold settings. So then, when we do this, then there are two questions that arise. So the first question is the following: can spectral data detect the presence of orbifold singularities? In other words, can a manifold be isospectral to a singular orbifold? And well, this first question is not non-trivial, and so so some people have tried to give some answers, and there are some results about it. But also there is another question related to the spectral geometry of orbifolds. The following is, the other question is the following: can spectral data of orbifolds with singularities be used to distinguish them from each other? In this talk, I will try to focus in the first question, but of course there are many other results related to the second question. Okay, so now that I have just give a brief idea of what I am interested in and what we are going to see today in this talk, just then let's start with a bit of the background on orbifolds. And okay, so to define formally an orbifold, then I need to start defining what an orbifold chart is. So an orbifold chart over a topological space is just a triple where here U tilde is a connected open subset of Rn. G sub U is a finite group acting effectively on U tilde by isometries. The map pi U from U tilde to U, where the set U is open, induces a homeomorphism between U and the quotient space of U tilde by the action of this finite group G. So this is a orbifold chart. And now we can talk about embeddings from one orbifold chart in another orbifold chart. And an embedding lambda, in this case for orbifold charts, is a smooth embedding between the charts U tilde and U tilde prime, such that this diagram commutes. And here, just this diagram basically is telling us that the embeddings behave well with the action of the groups GU and GU prime. Okay, so Now, we will say that two charts are compatible if for each point living in the intersection of U and U prime, there exists an orbifold chart, U double prime around X, and embeddings from this chart double prime to each of these original orbifold charts. And so then with this, we now are ready to define what an n-dimensional orbifold is. So an n-dimensional orbifold is a second countable Hausdorff space together with a collection of compatible charts, which are, this collection is called an atlas, where the images form an open cover of X. Now, we now can define what the abstract isotropy type of a point in an orbifold is. So this is defined as the isomorphism class of the stabilizer or isotropy group of a point X tilde living in the preimage of X under pi under the action of the group finite group G on U tilde. And we will say that a point in an orbifold is singular if isobar, which is the abstract isotropy type, is non-trivial, and otherwise we will say that a point is regular. Okay, so here is a lot of definitions, but okay, so let's look at some examples of this definition, so to have a clearer idea of what we were defining before. So first of all, as I said, a manifold is, an orbifold is a generalization in some sense of a manifold. So then a manifold is an orbifold, indeed, without singular points. So, and what is the local, the charts? Well, orbifold charts, well, in this case, they are obtained by the normal charts of them associated to the manifold. And to each orbifold chart, the group that is acting there is the trivial group. Yeah, so trivially a manifold will be our first example of an orbifold. And two more interesting examples are the ones that I'm showing here, which one is the teardrop, as you can see why it is called a teardrop. And also we have a square as an example of an orbifold. And I'm showing these two examples because here we can see three important types of singularities, or the three types of singularities that will appear in orbifolds of dimension 2. So these are cone points, mirror reflectors, and dihedral points. So, okay, so let's start then looking at this teardrop. So let's consider, so here basically the interesting point in this teardrop is this point X, which is our singularity. All the other points will be regular points. And so in this case, I'm taking, we can take an open set around this point X. So let's denote it U. And so we can locally model this neighborhood by, if we take, for instance, U tilde being an open ball in R square, then we can let the group Z2 acting by rotations on this set. And so we can see then that the center of the ball is fixed under the action of this group G. So in this case, so again, to define the isotropy type, the abstract isotropy type of X, we need to look at an element in the preimage. And in this case, the only element in the preimage of this point X is X tilde. And this is fixed by the whole group. Okay, so this is just for the teardrops. Now for squares, we have now here, let's look at different other kind of singularities. Sorry, here I just forgot to say that this is of course a cone point and is an isolated singularity. Now, if we take an open set here, U around in this part, as I'm showing in this picture, so then we need to consider two types of singularities, which in this case, one is Z, and the other type of singularity that we might look at is the point Y. So how can we model this locally, this set U? We also can take, in this case, an open ball U tilde. And in this case, we can let gamma 1 and gamma 2 being two reflections acting on them, on this ball. And so we can identify one side of the ball to the other side, to the other half side of the ball. And what we see is that, for instance, if we look at the point at the center of the ball, so this point is fixed under the action of this rho 1 and rho 2. So the whole group that is acting in here is the dihedral group of order 4 that happens to be an abelian group Z2 cross Z2. And so in this case, because this is Z tilde is fixed under the action of the generators of this dihedral group. So here the abstract isotropy type of Z is the whole group Z2 cross Z2. But now, let's look at Y and what happened with the pre-images of Y under pi. So here we have these 2 points. And if we look at whatever of these 2 points, Y1 tilde or Y2 tilde, then we will see that any of these 2 points is fixed under the action of rho 2. So in this case, the abstract isotropy type of Y will be Z mod 2. So as you can see in this case, the abstract isotropy type is independent of the element in the pre-image that I'm looking at. Okay, so then these are two very basic examples that allow us to see all the definitions, well, some of the definitions that we gave before. But well, so this is a local picture of orbifolds. There is a more general picture of orbifolds. So we can think of orbifolds as global quotients of manifolds by compact Lie groups. So in this case, an orbifold will arise as the quotient space of the orthonormal frame bundle of the orbifold by the action of ON. And the action of ON has finite isotropy. So this way to think about orbifolds is nice because this will allow us to stratify our orbifolds using the isotropy at the points in the orbifold charts. So here, if Q is a quotient map, then the isotropy type of a point P in the orbifold is just the conjugacy class of the stabilizer of the point P in the pre-image of this point in ON. So here I just want to say that if we compare with the abstract isotropy type, then this is a much finer description of the isotropy type of a point in an orbifold. So a smoother stratification of an orbifold is a locally finite partition of the orbifold into locally closed manifolds, which we will call O strata. Now, we will say that 2 points in the orbifold are isotropy equivalent if they have the same isotropy type. And we can show that, well, this will define equivalence relation. And the connected components of the isotropy equivalent classes of the orbifold will form a smooth stratification of the orbifold. So now locally also we can obtain a smooth stratification by just taking the action. So the action of the local groups will induce a stratification in both U and U tilde. And now given an stratum, U tilde stratum N tilde, we define the isomax of the stratum N tilde as the set that contains all the elements in the isotropy type of N tilde, such that N tilde is open in the fixed set, point set of G. I will say more later with one example, so that it will be clearer what this isomax is. And an stratum N tilde is singular if iso N tilde is non-trivial, and we will say that it's primary if isomax and of n tilde is not empty. So here we say that the stratum of, so given a stratification, we can again like divide our strata into a singular strata and regular strata. And here, so this primary thing is just a bit subtlety, but we will need it for our results. Okay, so now if we can also define or assign a Riemmanian structure to an orbifold, and it is defined by giving the local cover U tilde for each orbifold chart an invariant Riemmanian metric. So in this case, we just let the actions of the groups, local groups, being isometries. And here the Riemmanian orbifold, we will say that is an orbifold together with a Riemmanian structure. Okay, so now let me just give an example of this stratification. So this figure is basically the figure that I presented in my first slide. Yeah, so this is just the quotient of the this wallpaper by the action of its group of symmetries. So then let's see what the singular strata are. So the singular strata consist of the point of the sets given by the point X, the point Y, and this green set, which is a Z. And all the regular stratum will be the blue part. So now in here, I'm just, instead of putting again the picture, here is, this is like a more simplified version of the wallpaper that we saw. So then we have here, remember that we have here the two mirror reflectors. So these will be the groups that this will generate a group of the dihedral group of order 6. And if in this case, the isotropy type of Z, as we said before, so here this comes from just the rotation by 2 pi over 3. So this is this point is just it comes from the image of pi on this point at the center. Now, if so this is generated, the group, the isometry, sorry, the isotropy group of X is just the group generated by the composition of row 2 and row 1, which is Z mod 3. And in the case of the isotropy type of Y is generated by the two reflections. Yeah, so here again we take a reflection along this plane and another reflection along this plane, and these two will generate the group of D6, which is the dihedral group of order 6. Now here Z is just basically comes from the set of fixed points by the mirror reflections. So here then, as iso Z will be generated by row 1, which is Z mod 2. And isomax, basically, again, we need to think about all the elements which in which this subset, this stratum is open in the subset of elements fixed by an element of the group. So in this case, for instance, isomax of X consists of 2 elements, row 1, row 2, and its inverse. And similarly for isomax of Y, and for isomax of Z is row 1. So as you can see, in general, for singular stratum, isomax is never going to be a group, but it's just a set of elements. Okay, so so this is just to say something about the orbifolds and this stratification. So this will be, it's part of what we elements or of the ingredients that we will require later to say something about the spectral geometry of these objects. So now let's go back, or let's go to talk about the spectral geometry on the trivial examples of orbifolds, which are manifolds, and let's talk about them because these are the most studied orbifolds in spectral geometry. So so let's start with that. And so given a compact Riemmanian manifold of dimension d, it is well known that the Laplace-Beltrami operator has a discrete spectrum with finite multiplicities, and the normalized eigenfunctions phi j are smooth and form an orthonormal basis of L2 of M, and the fundamental solution of this heat equation or heat kernel has the following form. So here we have this expression, so this is just general or common knowledge. The trace of the heat kernel on functions on M, or simply the heat trace, has an asymptotic expansion as t tends to infinity, given by this, where here the coefficients aj's are integrals of polynomials over M, and these coefficients are the invariants that we call the heat invariants. Okay, so as I said, so we have, it's been well, these results are well known, and indeed we can not just think about the Laplace, Laplacian acting on functions, but also we can think about the HodgeLaplace operator acting on the space of p-forms. So Gaffney in '58 showed that there is a unique fundamental solution of the heat equation given by this expression. So here, so we can see that here we can put these eigenvalues and eigenfunctions are indexed by also by the value of p, so which is just the p form we are looking at. And there is an asymptotic expansion of the heat trace as t tends to 0, which is given by this expression as well. So here d is the dimension of the manifold. And again, these coefficients are integrals over M and are called the heat invariants for p forms. And here we just have to remember that in the case of zero forms, the zero forms are just functions. So in here we have that AJs that I showed before for the Laplace-Beltrami operator coincides with the AJ, 0. Okay, so now let's look at the first heat invariants for delta 0 and delta 1 acting on functions and on one forms. So for instance, so the first heat invariant for functions a0, 0 is just the volume of the manifold. And for one forms, it's a0, 1 is just the volume of the manifold times its dimension. Now, for the case of the second heat invariant a1, 0, this involves now the integral over M of the scalar curvature of the manifold. And a1, 1 in this case is a1, 0 times d minus 6. And so on. So in here, for instance, I'm just put another heat invariance to see how these expressions for the heat invariance become more complicated as k, well, in this case, j increases. So here, for instance, we can see that for a2, we will have some geometric quantities like the scalar curvature, the norm of the Ricci tensor, or the norm of the curvature tensor. But yeah, but here will be important to remember how the first two heat invariants and in zero forms and one forms are related. Okay, so so now this is just, it was nice for a good introduction of our the theory of orbifolds and the spectral geometry on manifolds, which is a special case of orbifolds. But for the rest of the talk, we will be interested interested in to give an answer to the following question. So as I said in the beginning of the talk, we are interested in trying to see if we can hear the singularities of the orbifold. That is, can spectrum data detect the presence of orbifold singularities, in particular in dimension 2 and 3. So that means, can a closed Riemannian be isospectral to a singular closed 3 orbifold? And also similarly, can a closed 2 manifold be isospectral to a singular closed 2 orbifold? So the idea in here is that we would like to obtain a asymptotic expansion for the heat kernel on p-forms and use the heat invariants for p-forms to distinguish orbifolds from manifolds. Okay. Right, so now let's start talking about the spectral geometry, what is known about the spectral geometry for orbifolds. So in 1995, Vucikovic showed that the HodgeLaplacian of an orbifold has a discrete spectrum, and each eigenvalue has a finite multiplicity, and the normalized eigenfunctions phi k, p are smooth and form an orthonormal basis of the space L2 of eigenfunctions on the orbifold. Now in 1990, Xiang showed a special case indeed for the closed Riemannian orbifold. So this was a previous work that was generalized in 1995 by Vucikovic, but Xiang showed for the first time results for Riemannian orbifolds, and in particular show the same result for that Vucikovic showed, but for the case when the p is equal to 0, that is for functions, and when the orbifold has a strata of codimension at least 2. In this case, on that time, orbifolds were not called orbifolds, but were called B manifolds, and in particular, they satisfy this condition that the strata has a codimension at least 2. Okay, so we will say that we denote by spec of O the sub P, denote the spectrum of the Hodge-Laplace operator acting on P forms, then given to orbifolds O prime, we will say that they are P isospectral if their spectrum are the same. Okay, so then let's start with the special case, P equals 0. So here, then we will have the following definition. So let O be an orbifold, and then a function K from this domain to R is a heat kernel if it satisfies the following condition. So K will be continuous, as is C1 in the first variable and C2 in the second variable. Also, this function satisfies this equation where delta sub x is the Laplace-Beltrami operator with respect to the second variable. And also, this limit is satisfied for all x in the orbifold. A result also obtained by Xiang in the 90s is the following. She showed that if a heat kernel exists, then it is unique, and it is given by this expression. So building on these results, Dryden, Gordon, Greenwald, and Webb in 2008 obtained a very nice theory which allows us to, that basically says that we can hear in some cases the singularities of an orbifold. And this is what we might call the parity theorem, and you will see why. So here, so the theorem says the following. If the orbifold is even dimensional or respectively odd dimensional, and if there exists an odd dimensional, respectively even dimensional primary singular O stratum n, then the orbifold cannot be zero isospectral to a Riemmanian manifold, right? So this theorem says basically that If I say have a manifold of dimension 3, then I can hear singularities in dimension 2 or dimension 0. And also, if I have, in the case of the, so we are interested in orbifolds of dimension 2 or dimension 3. So if I have an orbifold of dimension 2 and I have a one-dimensional stratum, then I can hear this singularity. So that's what it is called the parity theorem. Yeah. Also they prove the following. So as I said, so this theorem then say kind of things if we have inverse parity of the stratum with respect to the dimension of the orbifold, then we can hear it. But what happened, for instance, in the case when we have a stratum of the same parity as the dimension of the orbifold? So the case is, for instance, of orbifolds, two orbifolds with k points of different orders, because k points basically are zero singularities, right? However, they were able to say things, although, well, this is a big theorem, but also with the heat invariants, they were able to give some results. And what they show is that, so this, they define this spectral invariant C, and they show that it is a complete topological invariant for the class of closed locally orientable orbifolds, and besides, Z distinguishes them from smooth surfaces sigma with the Euler characteristic of the surface bigger than or equal to 0. Yeah, so still there are some partial results for the case of when the parities coincide in for the spectrum and the dimension of the orbifold, but not in general for all the cases. Now, from these previous results, the spectral geometry, it is not clear, for instance, what happened if the dimension of the orbifold is 3 and there is only one-dimensional strata. So the idea then is that we want to fill up these gaps and see what happens. Now let me define what a double P-form. So let's start saying what a double P-form to then define what a heat kernel for P-forms on orbifold is. So a double P-form is just associate with each point x, y in the Cartesian product of two copies of the orbifold, an element on the tensor product of the pith exterior algebra of the cotangent space at the point x in the orbifold and the cotangent space at the point y of the orbifold. And so the wedge product is defined in this way. So now with this in mind, we can define then what a fundamental solution is for the heat equation. So we will say that K is a heat kernel or fundamental solution of the heat equation if it satisfies these following conditions. So K is a double it's a double P-form for any T in the open interval 0 infinity. K is continuous in the three variables, C1 in the first variable and C2 in the third variable. Also satisfy this equation for each x in the orbifold, delta sub y is a HodgeLaplacian with respect to the variable y. And for every continuous P-form, also we have that the convergence of this limit. So it's not difficult to show that then there is a unique fundamental solution of the heat equation, similar to the case of manifolds. For the case of orbifolds, we will have an expression in which here now we replace functions by double P-forms. So this will be a double P-form. Now our first theorem says the following. So let O be a closed Riemannian orbifold of dimension n, and we will fix P between 0 and n. So the heat trace of the heat kernel has an asymptotic expansion as t tends to 0, given by this expression, where here eta alpha is a partition of unity and h is just a parametrics. And here C12 means we will define also a kind of a inner product in the double P-form. All right, so now, so then we have this general result of the heat. We know that there is a heat kernel, and now we want to find the heat, to get an asymptotic expansion for the heat trace as t tends to 0. So now that we have this result, so let P be in 0 or 1. Then the heat trace has an asymptotic expansion as t tends to 0 given by this expression. And here I have to maybe be going slowly because this is a bit long statement of this theorem, a bit long statement. So here I just want to maybe just point out that this part I naught is basically has to do with the contributions of the regular points, and the second summand, the other summand, and in the expansion has to do with the singular points. So here, as I said, just I naught here just encodes all the heat invariant defined as for manifolds. Yeah, and here SO it denotes the set of all singular strata of the orbifold, and iso n bars is just the order of the isotropy type of the stratum n. All right, so here just remember that any point in the stratum we define an equivalence relation, and then all the elements in the same stratum have the same isotropy type. Okay, now so this statement continues. So we have here In is defined in this way. So In, so that means the contribution of the singular strata is given here. I want you to notice here the change in here is the dimension of the stratum, and before in here for the case of the manifold, here we have the dimension of the orbifold. And here we have some functions bjp, which basically these are sums of all the elements in isomax of n tilde. And here of the sum of all the over this set of the determinant of the identity minus here A sub G is the matrix which is induced by the action of G. So this matrix will act in the orthogonal complement of the tangent space of at X in the stratum, which lives inside of our orbifold. Yeah, and here these B tilde are functions which are polynomials that depend only on the germ of the Riemmanian metric and the isotropy action. And this expansion has the following form. So as you can see, so we might like condense a little bit more our expansion so that we can write it in this way. So here we have these other coefficients, say GP. And here, what is interesting is that then we see that there are half powers appearing, which it didn't happen, for instance, in the case, well, in this case, for manifolds, for instance, depending on what the dimension of the manifold is. So we think about the orbifold just being a manifold. Then in this case, if it is odd dimensional or even dimensional, we will just have either integer powers or half powers of T. But in the case of an orbifold, we will have mixed, we might have mixed powers. So indeed, basically this just noticing this, then we can understand why this parity theorem holds. All right, so this is just our general result, and we would like to apply it to say if we can hear the three-dimensional singularities, all the singularities for the case of three-dimensional orbifolds or two-dimensional orbifolds. So here let's R denote the rotation matrix in SO2, where here theta over pi is rational. And we will say that a simple rotation of angle theta is an element of SON, which is conjugate to a matrix of this form, where here, I'm sorry for the typo here, should be either K or, well, okay, so where I sub K denotes the K by K identity matrix. The group generated by a simple rotation act by rotation on a single plane. Yeah. And so this is our theorem. So let O be here. I have to say that we always are working with closed orbifolds, and so that means compact and without boundary. So here, even though I didn't put it explicitly, but we consider that this is compact, closed. So let O be an orbifold of the dimension d bigger than or equal to 2. Suppose that the singular set of the orbifold is non-empty and consists only of simple rotation strata. Then the orbifold can be distinguished from a closed Riemmanian manifold by its 0 and 1 spectra. And now just let me give, I'm going to sketch the proof of this theorem. So for that, the group generated by a matrix R theta acts by rotation in a single plane, as we said, with a fixed point set M of dimension d minus 2. So our strata will have dimension d minus 2. So for now, we will assume that we only have one stratum with isotropy of order M. Then it's easy to see that then the isomax of this single strata consists of all the elements generated by this simple rotation, apart from the identity. So then what we have to do, so here then the important thing is to try to see when the contribution of the singular strata appear in the expansion. And the first term where the contribution appear is in the term t to the, they appear as a coefficients of the t to the 1 minus d over 2 in the 0 and the 1 form asymptotic expansion. So then in this case, we have to compare the asymptotic expansion of a manifold, the coefficients of these powers for A10 and A11 with those of an orbifold, which in this case will be Z20 and Z21. So then by the asymptotic expansion of the heat trace, we have the following. So again, I just want to go back a little bit and see that we said that this is the contribution of just the regular points, and this is the stratum. So we need to see what these things are, what these part I n are. Okay, so then we have to compute this in. So in this case, we are assuming that we have only one stratum. So then this is equal to this expression. And so in this case, we need to compute these functions. So in this case, it's easy to see that the computation of these 0, 0 are the same in the case of a cone point in an orbifold of dimension 2. So again, like the orthogonal complement, so the matrix which acts on the orthogonal complement will be just the rotation matrix of living in SO2. So then, and this is the same one that acts for the case of orbifolds of dimension 2. So this is a kind of very like simplify our calculation. So the first coefficient is computed in this way. So we have here C2, 0 is just the coefficient as for manifolds. So the contribution of the regular points plus the contribution of the stratum. And in here, so B0, 0 of tilde will be just 1. So here you just need to compute, in this case, the determinant as I showed here. And the determinant is given by this expression when, and we can simplify this expression using Bernoulli polynomials. And what we obtain is this expression. Now we compute the coefficients in C2, 1. And here again, part of in our results show that this B01 is just the trace of the original matrix R theta, or the simple rotation matrix. Yeah, not the R theta, because R theta is just defined as the matrix living in SO2, but the simple rotation matrix. So in this case, when we compute, we do, again, similar tricks, applying some Bernoulli polynomials, and we obtain this other expression. Now, the only thing that we have to notice now is that in the case of a manifold, if the orbifold was a manifold, then our expression reduces just to, so we already saw in the table that I showed before that the term A11 is equal to D minus 6 times A10, which implies that for a manifold, also this needs to hold. Yeah, so if for any manifold. And now the result follows by showing, in this case, that when we try to see what the relation between Z21 and Z20 for an orbifold is with this special kind of stratum, then this will be always an inequality, yeah? And also we have to notice that if we add more than one stratum, then the contribution on C21 and C20 will be always positive. So the inequality will still hold. All right, so then this is just the proof of the theorem. And as a corollary, what we get is the following, which says that the 0 and 1 spectra distinguish surfaces from singular to orbifolds, and also the 0 and 1 spectra distinguish 3 manifolds from singular 3 orbifolds. And how did we get this? Well, of course, it's using this result plus the result of the parity theorem. So whenever we have, it doesn't matter what the parity of our stratum is, we can hear it. And all right, and I think I will finish here, but before I just want to say thank you, and I wanted to show the picture of the beautiful women that are, well, here are working in this project, and this is a picture of where this project started a year ago. Thank you very much.
Thank you very much for the very nice talk. Let's clap for the speaker. I would like now to invite participants to ask their questions, either by speaking out or writing in the Zoom chat. Please go ahead.
Let me ask a question. So at least in the situation when there are strata of codimension 1, I guess you need to impose some boundary conditions. This is the first part of the question. And the second, I just don't know, I've never worked on that. In the case of strata of high codimension, is it true that the Laplacian is essentially self-adjoint always?
Yes. Yeah. So this is the work of Busikovic. Mm-hmm. And for the other question, yes, we show, well, I didn't put it here, but we also took this bound, when the codimension of the strata is 1, we rectified for some boundary conditions, and everything works okay. So this is already have been studied by other people, by Park, and so the results coincide with the results of Park.
Yeah, and what kind of boundary condition you took in the case of codimension 1?
I think we took mixed boundary conditions, and well, this is in the work of Park, or I think absolute boundary conditions.
Absolute boundary.
Yeah.
Okay, thank you.
Anyone else? So are any of the results you obtain new in the case of manifolds or not?
No, so these are just for orbifolds, and yeah, so the idea of this project was try to obtain results for try to distinguish orbifolds from manifolds.
Sure.
And we also obtained some results to distinguish orbifolds among themselves. So there are some partial results and other results for the special cases when the codimension of the stratum is not d-2, but d-4. The stratum is d-.
Thank you.